hopefully. Okay, so systems of equations. So that's chapter 9. And today we'll do 9.1. These are the two equations, two unknowns. And I'll refer to them as 2 by 2 systems. Two equations, two unknowns. And 9.2 would be 3 equations. Three unknowns. They're 3 by 3 systems. Does that sound good? And by the way, we'll just keep them linear, I should have said. Linear equations. So systems of linear equations, that's even better. Okay? So let me just start you off with an example. Most of you, I mean, all of you have done systems. Some of you might still remember how that's done. So I'm just going to give you a simple example. Two equations, x minus y equals 5, and 2x plus y equals 1. So, again, if I just ask you to solve the top equation, how many solutions does the top equation have? Just x minus y equals 5. How many pairs of numbers? 2? Give me an example. Yeah, there are 2 numbers, but how many different pairs of those numbers can I have? Infinite, right? There are infinitely many numbers subtract to 5. And then there are infinitely many numbers where double of the first plus the second equals 1. So both of those equations separately have infinitely many solutions. We're looking for the solution that both of these equations share. Okay, the one that works for both. And since these are the 2 lines, if I graph them, they're the 2 lines. Basically, we're looking for the point where they intersect. So how many points can we have when 2 lines intersect? 1, so we're going to get 1 solution. If I graph them, you can always solve the equations by graphing. Now, that's not really the best choice, because if your solution's so weird, then it's hard to precisely graph them. But this one I can graph pretty easily. I can find the x and y intercepts, right? The x-intercept is 5. The y-intercept is -5. So here's the first equation. The second equation, y equals -2x plus 1. So the y-intercept is 1, and the slope is -2, something like that. So this would be the solution, the point where they intersect. So if I did that very precisely on a nice graphing paper, and if that point was actually in one of the square corners, then I'll be all happy, and that'll be my solution. Of course, it doesn't happen like that all the time, but at least we know something positive for x, something negative for y, most likely. Okay. And then if you think about this, these 2 lines just intersected, so we got 1 solution. Lines don't have to intersect. If I have 2 lines that are parallel, they will not have a solution, right? Or if I have 1 line as a constant multiple of another line, so they overlap if I graph them, then they'll have infinitely many points where they intersect. Okay, so there are 3 options: 1 solution, no solutions, or infinitely many. But let's just solve it analytically. And the first technique that we talk about in solving this types of equation is called substitution. And again, the whole idea behind solving systems of equations is to keep reducing the number of equations and the number of variables. So what we're trying to do, we're trying to go from 2 equations, 2 unknowns, to 1 equation, 1 unknown. So I'll get nice linear equation. I can always solve that. So the way we do this, we're going to pick a variable in one of those equations. So I have 4 choices, right? I can pick x in the first, I can pick y in the first, I can pick x in the second, I can pick y in the second. So choose one of those variables and solve for it, okay? So the first step, solve for one of the variables in terms of the other. So just make your choice. Doesn't matter which one you. I mean, sometimes it's easier to solve for one. So which variable would you like to solve for? In which equation? Why? That's the worst choice. Okay, he asked for it. So 2x equals 1 minus y. So x equals 1/2 minus y over 2. That's all Will's fault. But you can solve for, the rest of you can just do it normally. So then, the second step would be to substitute into the other equation. So we're going to take this x, and we're going to plug it into the other equation. So if we're solving in the second one, plug it back in the first. So we'll get 1/2 minus y over 2 minus y equals 5. Right? Okay. So subtract 1/2 from both sides and combine the like terms. So you get negative 3/2 y equals 5 minus 1/2 is 9/2. Right? Doesn't have to be that nasty. And then just multiply both sides by 2/3. So all of that cancels. Y equals 2 and 2 cancels. Negative 3 goes into 9. Negative 3 times. So y equals negative 3. You'll get negative 3 no matter how you approach this. Y will always equal negative 3. Right? So now, since we found y, now we can go back and find the other variable. So since y equals negative 3, I can take it and I can plug for y into any one of these equations. First, second, that doesn't matter. So if I plug it in the first equation, I get x minus negative 3 equals 5. So that means x plus 3 equals 5. So x equals 2. Right? So the solution here is 2, negative 3. Those are the coordinates of that point that we found. It kind of looks like 2, negative 3.
So that quiz last night, we had a quiz that required these systems.
We didn't have a quiz last night.
No, I was just grabbing the first 7 hours.
Yeah.
All this, I wasn't supposed to do it. When I stopped, so I went back for it, and so I could do it without the next time.
Right? It's not due till next Sunday. Or do I have the dates wrong? Lewis, get it done early. Okay. So that's one technique called substitution. Another technique is elimination. So I'll do the same problem using the elimination technique. So the idea for the elimination is that we know that if you have an equation, you can always add the same quantity to both sides of the equation. right? I can always add 7 to both sides of the equation and so forth. So it is perfectly legal to add two equations to each other, because if I add left sides and the right sides, those equal signs tell me that I'm adding equal parts anyway, so that's okay. Now see what happens if I just go ahead and add these two equations. X plus 2x gives me 3x, negative y plus y cancels, 5 plus 1 equals 6, right? So as I was saying, it's always beneficiary for us to turn multiple equations with multiple variables into single, okay? So then you solve that, that's trivial, x equals 2, right? And then we can go back and solve for y by plugging this back into any one of the equations. So find y, 2 minus y equals 5, then you solve it, y equals negative 3. So the solution is 2, negative 3, as before. Okay? And the reason why it works so nicely, because we had two variables that have same coefficient, opposite signs. So y's had coefficient of 1, positive 1 and a negative 1. So when we add, they just go away. Now, if they don't have those coefficients, we can always work around that to make the coefficients equal. But that's the key. You want to have at least one variable to have this matching coefficient. So when you add the equations, one of the variable goes away. So I'm going to give you this example. (2x plus 4y equals 11), and then 16x minus 3y equals negative 1. Now we're going to get some nasty answers. Okay. So when you see an equation like this, solving this by substitution is going to be ugly, right? Because no matter which variable you solve for, you're going to have fractions. Agree with that? There's no easy choice. So when you're faced with things like that, the elimination is the better route to go. All you have to do is just to pick a variable. Which variable would you like to kill? X or Y? Okay, Y. Why? Okay, no reason. That was just random. Okay? Doesn't matter which one you kill. So 4 and a 3. So basically what you're thinking about, well, if I was dealing with fractions and I have to find the least common denominator for 4 and 3, what would that be? 12. So that would be that matching coefficient that I want to achieve. So I want to have a positive and a negative 12, so they will cancel. So that means I'll have to multiply the first equation by 3 and the second equation by 4. Because if I do that, the y's will have matching coefficients, opposite signs. We could have gone after x, just multiply the top equation by negative 8. But again, doesn't matter. You'll get the same every time. So what do we get? So that's our system. Now it is 6x plus 12y equals 33, and then whatever that is, 64, yeah? Minus 12y equals negative 4. Yeah, so add both sides. 6 and 64 give you 70. Y's cancel. The other side, 29. Right? So x equals 29 over 70. How's that? So how do I find y now? Okay, so I can take that x, and I can plug it in anywhere I want. I'll just probably go for the first one. Well, doesn't matter. So if I take that x and I plug it into the first one, we're going to get something really ugly. 2 times 29 over 70 plus 4y equals 11, right? So right away, 2 and 70 cancel, so that's 35, right? So here's your equation. How would we go about solving that? You have 29 35th plus 4y equals 11. What should I do? Subtract that constant? Yeah, we can do that. Just deal with the fractions here, I guess. You can multiply both sides by 35 to simplify that, but it'll just be ugly either way. So I need to make common denominator 35, right? 11 times 35 is what? 385 minus 29. Is that right? So, what is that? $85 minus 29, 56. Really? Is it 56? Yeah. Okay, so then it's divisible. It's divisible by 4. We can divide this by 4. 4 goes into 356, exactly 89 times over 35, right? So 2 and 19 35th. Is that right? Is 89 correct? Well, because 90 times 4 is 360. 356 is 1 less, so it's not 90, it's 89. Yeah. So then the solution, what was the x again? 29 over 7. And the y is 2 and 19 35th. So, if I say this, finding x was okay. Finding y was a little nutty, right? Do you know that? Finding x was a whole lot easier than finding y. So there is another way of doing this problem. So you all found x. Is everybody happy with how we found x? Well, we can find y the same way. We can go back to the original problem and eliminate the x's and solve for y. This will avoid all this substitution and messing with fractions. Because I can do that. Nothing prevents me from repeating this problem and eliminating x. The way to eliminate x, I'll just have to multiply the first equation by negative 8. 2x plus 4y equals 11. Keep the second equation the same, right? And then just do the elimination on the x. So we have negative 16x minus 32y equals negative 88. And then 16x minus 3y equals negative 1. Right? So if I add this, the x's cancel. Negative 32 plus negative 3 is negative 35y, while the other side is negative 89. Right? Yeah. So then y equals negatives cancel. Y equals 89 over 35. And that's exactly what we found. But we didn't have to do all that solving a more complex equation. So it's okay to eliminate x to solve y and then go back and eliminate y to solve x. Yeah. How's that? So we can do that every time. So let's do this example. 2x minus 4y equals 11, and then 16x minus 32y equals negative 21. Oh, the earlier one? Okay, so how would you like to solve this one? Multiply the top by 8? 8 or negative 8? Negative 8, because we want the signs to change, right? So then we'll get negative 16x plus 32y equals negative 88. That looks very familiar. And then the next equation stays the same, right? So what happens when we add them? Yeah, x's cancel, y's cancel, we get 0, while on the other hand, it's negative 109. That's impossible, so no solutions. So that means that both lines were parallel. Okay? So these are the parallel lines. No solution. So that's all we have to say. If we ended up with a true statement, let's say you do your elimination and get 0 equals 0, which is a true statement, that means everything works. So in Fleming solutions, the two lines overlap. So the solution to that system is just the equation of one of those lines. It's kind of silly. Whatever makes one of the equation work, we'll solve the system. We'll make both work. Okay? Four x plus 3y equals 11, and then negative 5x plus 2y equals 15. So, how would you like to proceed? Substitution, elimination. Elimination, well, which variable would you like to kill first? Let's do x. All right. So how do we kill x? What do we need to multiply top and the bottom by? Why negative? You said negative 5? Yeah, just 5, right? And just 4, because they already have opposite signs. And this is if we're killing x. If we were killing y's, we would have to do opposite signs, because they have the same signs right now. So 20x plus 15y equals 55. And then negative 20x plus 8y, right, equals 60. So when you add these two equations, you get 23y equals 115, right? And I believe if you divide both sides by 23, y is just 5, right? Okay, so if y is that pretty, it's probably easier to go back and plug 5 into one of those two equations. Okay? So finding x. So if I take the first equation, 4x, plus substitute 5 for y, it's 3 times 5, equals 11. 4x plus 15 equals 11. So 4x equals negative 4, x equals negative 1. Is that correct? How's that? Is that good? Okay, so 2 by 2 is a pretty straightforward. And you can either use substitution, elimination, whatever. Unless you specifically told to use substitution. But on my math lab, there's no way for them to know what you used. On the exam, I don't think I'll care much. But I mean, you can use both of them are pretty. I mean, substitution, elimination is a little more useful, I think. All right, let's consider a 3 by 3 system. That's always fun. So here's a fun example. X plus y minus z equals 6. So we have 3 equations, 3 unknowns. Negative 2x plus 3y minus 2z equals negative 1. And then 3x minus 4y plus z equals 1. Okay. This is still linear equations. There are no exponents. If we were to graph each one of those equations, instead of getting a straight line, we'll be getting a plane. So the actual graph of each one of those equations is 3-dimensional plane. Because you have x, y, and z, so it's a 3-dimensional shape. So there are a lot of things can happen with planes, right? I mean, if you start picturing that, you can have 3 planes parallel to each other, so that doesn't work. You can have planes intersecting, something like that. You have a 1 plane going here, and then you have a 1 plane. Does that make sense, this pretty picture? These are the 3 planes, but they don't have the point in common, right? Okay. It's challenging to make 3-dimensional drawings. Wait till Calc 3, you're going to have fun with that. We're going to use the Classroom 117. We're going to buy 3D chalk, and you're going to be wearing a 3D glasses as I'm drawing the 3D. Oh yeah, it's going to be fun. The 3-dimensional shapes. Or you can, you can have 3 planes that intersect in 1 point. So that's okay. So that's what we hope. Oh yeah, 3D. Go to Walmart. They sell them. It's 3D chalk with glasses. Yeah. See, live and learn. Now, it's going to be impossible to solve this thing by graphing. It's just insane to be able to plot it pretty. So the first approach to this problem is, again, we'll focus on this for a while. Each additional section will develop a newer and cuter way of solving these. But the first brute force way is to pick a variable and kill that variable in any 2 of the equations. So what I mean by that, let's say I don't like the x. So I'm going to go ahead and kill the x in the second equation. So all I have is y and z. And kill x in the third equation. So all I have is y and z. So then I have 2 equations with 2 variables. I already know how to solve that, so I'll solve them separately. So I'm going to reduce 3 by 3 system into 2 by 2, solve 2 by 2, and then go back and find the third variable. So if I can reduce this to just 2 little equations with 2 variables, so let's say y and z, so I can find y and z, and when I know y and z, I can plug them back and find x. Now, I just said x because, that's what I saw first. You can kill any variable that you like. Because look, if I take, for example, third equation and the first equation, if I just add them, the z's will go away. Right? You agree with that? So if I do that, if I go, okay, equation 1 plus equation 3, so this is x plus y minus z equals 6, and then 3x minus 4y plus z equals 1. If I just add them, I'll get 4x minus 3y equals 7. Right? So I eliminated one of the variables. Okay? So I need to do another pair of equations where I eliminate the same variable. And what I see, and again, this is not the unique way to solve this system. There is no, you have to do these steps to solve systems. That's kind of a weird part about it. As long as you keep your stuff kind of legal, you might get to the answer. Now, what I see right now, if I multiply the third equation by 2, and I add it to the second equation, these will cancel as well, right? So then I'll have another equation with just x and y. So I'll do that. I'll say, okay, equation 2 plus 2 times equation 3. So equation 2 is negative 2x plus 3y minus 2z equals negative 1. And 2 times equation 3 would be 6x minus 12y, right? No, not 12, 8. I'm multiplying it by 2. So 6x minus 8y plus 2z equals 2. Is that okay? So just multiply the third equation by 2. And if I add them, what do I get? 4x minus 5y equals 1. So do you have any questions? I see some dirty looks, but questions on how I got that. This is not the only way to do this. Again, I mean, I can do this. I can go after x's first, as I was initially talking about. I can go after y's. Doesn't matter. As long as you're able to kill the same variable in 2 of the equations, as long as you can come up with 2 different equations with just 2 variables, then we're in good shape. Because now I have a whole new system. Right? I can solve this system, can I? What would be the best way to solve this system? Yeah, to any one of them, right? So let's do the bottom one. So it's 4x minus 3y equals 7, and the negative 4x plus 5y equals negative 1. You add them, x's cancel, 3y equals 6. 2y. Yeah, 2y equals 6. So y equals 3. Right? Now y equals 3. I can take that, substitute into one of those equations to find x. So we'll get 4x minus 3 times 3 equals 7. So 4x minus 9 equals 7. So 4x equals 16. Right? So x equals 4. So we got that. So we found x and y. So I can go to the first equation, plug x and y in, and then find z. Does that make sense? So again, the job was to reduce 3 by 3 into 2 by 2, solve 2 by 2, and go back and find them, the remaining variable. So then what was the first equation? X plus y. So substitute 4 for x, 3 for y. So that's 7, subtract negative z equals negative 1. So z equals 1. So the solution is 4, 3, 1. It's not an ordered pair, it's an ordered triplet. It's a point in 3 dimensions, x, y, and z. So, but it's the same concept. We order them like we order regular ordered pairs, alphabetically, x, y, z. How's that? Again, I didn't have to do it like that. I think I already mentioned it a few times. Not really. Well, you see, the easiest way, this was a very special equation because I had one of the equations had all ones for the coefficients, basically, right? Because it's always easy to use 1 to kill the rest. Because I have this x, if I multiply it by 2, I kill the second x. I have this x, if I multiply it by negative 3, I kill the third x. So it's always easy to use the coefficients of 1 for the killing. Does that make sense, what I'm trying to say? Yeah. So I could have, that's a very special equation. If you have one of the, out of 9 coefficients, if one of them is just 1, just use that one to start killing in that column, right? If we had y in the middle, kind of one coefficient, I can go back and kill the top one and the bottom one. Okay? And by the way, we can always rearrange the order of the equations. It doesn't matter how we write them. All right, let's try this one. Well, why don't you try that one? The nice thing about this equation, about this system, is that second equation is missing y already, right? So then just probably kill y in one of the other 2 equations, and then you have xz system. So already used, so this equation is ready for you. It already has only 2 variables. So which other y do you think is easier to kill? How would you kill the y? Yeah, just multiply top by 2, right? To get negatives. And then Adam will give you another equation with just x and z. And then you go and you solve. All right, well, I'm going to pause this fun video. Okay, so the nice thing about this equation is that y is already eliminated in the second equation. Oh, it's a bunch of over 17 numbers. There's like 10 over 17 and 21, 17, 23, 17. You got those? Some of those are negative, right? Okay. So again, we already have y eliminated, so I can use these 2 coefficients to kill the y in the third equation. So we'll just multiply 2 times equation 1 plus equation 3. So if I multiply first one by 2, I'll get 6x minus 4y plus 2z equals 8. And then it's 6x plus 4y minus z equals 7. Right? So if I add them, we'll get 12x plus z equals 15. So that's our new equation. And I'll take the original second equation in here. So that's negative 2x minus 3z equals 1. Right? So we'll use this 2 by 2. You know, I can multiply the bottom one by 6. So that gives me 12x plus z equals 15. And the negative 12x minus 18z equals 6. Is that correct? Yeah? Add them. Cancels. Negative 17z equals 21. So z is negative 21 over 17. Right? I can take that number, plug it back into one of these equations to solve for x, but I think it's easier to eliminate z's and solve for x that way. Just do the elimination on the other variable. So if I kill the z's, I'll have to multiply the first one by 3. I mean the whole thing by 3. And then this is negative 2x minus 3z equals 1. So that's 36x plus 3z. Is that correct? So it's 34x equals 46. So x equals, when you divide and reduce, 23/17. Right? I mean, I think most of you got it. And then solving for y, that's the painful part, right? You're going to take these two numbers and plug them into one of the equations that contain y. So let's say the first one. So if I do the first equation, it is 3 times z, 23/17, minus 2y, and then plus the z, so it's negative 21/17, equals 4, right? So this is, if you multiply that, that's 69/17, subtract 21, so that's what, 47/17 minus 2y equals 4. 48, yes, 48, thank you, just making sure, right? To make it easier, just multiply everything by 17. So this is 48 minus 34y equals, whatever that is, 68? Yeah. So you get rid of all the fractions, subtract, negative 34y equals negative 20, no, positive 20, right? And then divide by negative 34, y equals negative 10/17. And that's it. All right. Let's try this one. X plus y plus z equals 7. 3x minus 2y plus z equals 3. And then x plus 6y plus 3z equals 25. So 3 by 3, we want to make it into 2 by 2. Just pick a variable, which one you want to kill. You want to kill x's, y's, or z's. Again, it doesn't matter in this case because I have this first equation with just, it's easy to use the first equation in this case to clear out the rest. So, which equation, which variable you want to kill? All right, let's kill x. So first, to kill that x, the 3x will multiply negative 3 times equation 1 plus equation 2, right? So let me write it out like this. So it's negative 3 times x plus y plus z equals 7. And then the other equation was 3x minus 2y plus z equals 3. So when I actually multiply by negative 3, we'll get negative 3x minus 3y minus 3z equals negative 21. And then 3x minus 2y plus z equals 3. So the second equation didn't change. So when you add these two, the x's cancel. Then we have negative 5y minus 2z equals negative 18. Is that correct? Looks reasonable. So here's our first equation. Now, the way we're going to build the second equation, I can just go top by negative 1, add with the second one, right? I mean, third one. So the x's cancel. So I can do this. I can do negative 1 times equation 1 plus equation 3. So this is negative x minus y minus z equals negative 7. And x plus 6y plus 3z equals 25. So when I add them, what do we have? 5y plus 2z equals 18. Right? So if I actually solve this system, I can go ahead and add these equations right away because, you know, without looking any further, I see that the y's will cancel, right? And the z, so we'll get, well, 0 equals 0, so there are infinitely many solutions, right?
You gotta go back up.
I had this equation there twice, so let me. Here we go. Now, there are many ways to express this answer. These equations have solutions, and we want to know how to generate them. The way I understand that, just pick a variable, preferably one of these two variables, either y or z. Just pick one. Z, okay. So I'm going to solve for z. Solve for z. Okay, so how are we going to do that? So it's 2z equals negative 5y plus 18, right? If I take the second equation here, and then divide both sides by 2, z equals negative 5 halves y plus 9. Right? So this is the equation of a line that satisfies both of these. If I treat y as the independent variable, plug any values for y, it will tell me what the z has to be in order to solve that equation. Okay, so now I have z in terms of y. I also have to get x in terms of y. Y is y. Y is going to be my independent variable. But in order for me to get x in terms of y, I can get my first equation. I'm just too lazy to write all that out. So I can take my first equation and I can replace z with that expression. So then I'll have everything in terms of y. I can solve for x in terms of y. So if I do that, it is x plus y minus 5 halves y plus 9 equals 7. So I just replace z with whatever expression I got earlier. So I just want to solve for x. So subtract 9 from both sides. Combine these two. So it's 1 minus 5 halves is negative 3 halves. X minus 3 halves equals negative 2. 3 halves y, right? So x equals 3 halves y minus 2. So the solution here, it is 3 halves y minus 2. Y is y. Y is my independent variable. We're solving for everything in terms of y. And z is, what was that, negative 5 halves? Y plus 9. So this is my x, this is my y, this is my z. Sometimes we don't even use y, we'll just say, hey, let that be t, some dummy variable. So y equals t, z equals negative 5 halves t plus 9, and x equals 3 halves t plus or minus 2. So then t is your independent variable. Same thing here. So I can generate points. I can generate points on this curve. I can say, here's some examples of the solutions. Let y equal 0. That's an easy choice, right? So if I plug 0 for y, I'll get negative 2, 0, and a 9, right? If I plug 0 for every 9. This ordered triplet solves all three of those equations. Okay? At the same time, I can say let y equal negative 2, and if I plug negative 2 in for y, just give me negative 3 minus 2, so it's negative 5, negative 2, and then plug negative 2 here gives me positive 5 plus 9, it's 14. That's another solution to that system. So I can generate as many solutions as I like just by plugging numbers for y. Is that okay? All right, good. That's enough. Go do that quiz, please.